Section 2.3. Two topics today. Topic 1, limit laws or limit formulas. Topic 2, direct substitution. Now, topic 1. In section 2.1 and section 2.2, we found limits by using tables. Using a table to find a limit is called a numerical method. Numerical method works well, but it has some drawbacks. About a limit, remember two important conventions. Convention 1, as independent variable x approaches upon a. In this process, x is not allowed to take the point a directly. Convention 2, as x approaches a, no matter how x approaches a, function f should approach the same number. Otherwise, we say that function f approaches nothing, or the limit doesn't exist. X approaches a. There are infinitely many ways that x approaches a. So to determine whether a limit exists, essentially we need to make infinitely many tables, but this is impossible. So this is a drawback of a numerical method. The second drawback that I can see is your answer about the limit can be wrong if you make some mistakes in the calculation of the function values. The third drawback that I can see is it is sometimes difficult to find the exact value of a limit. For example, consider this limit. As x approaches the point 1, this function will approach some number. Can you exactly tell the value of the number by a table? Here, I have made a table. In this table, I let x approach the point 1 by taking on these points. By calculator, the function values at these points are these values. Now, from this table, as x approaches 1, I can tell function approaches this number. About this number, I can only tell the first 6 digits, 707106, because based on the last two numbers in the table, the last two numbers, they match only the first 6 digits. After that, the digits are different. So I cannot tell the digits after the first 6 digits on the limit. Okay, now what is the exact value of this limit? The exact value of the limit is square root of 50. What is square root of 50? This number. This number has infinitely many digits. So by a table, I cannot exactly tell this number. Now, based on this example, we can conclude that a numerical method by table usually only provides a guess of a limit and cannot give the exact value of a limit. There are some other drawbacks of using a table to find a limit. For example, using a table to find a limit is time consuming. Computing function values takes time. Now, in this section 2.3, we don't use a table to find a limit. Instead, we use limit laws to find a limit. I can see two advantages of using limit laws to find a limit. The number one is we don't need a calculator or a table. We just need a paper and a pen. Then we can find a limit. The second advantage is we can always find the exact value of a limit. In this book, using a table to find a limit is called a numerical method. Using limit laws to find a limit is called an analytical method. Here I summarize all the limit laws below. Law number one is the summation law. It says that limit of a sum is sum of limits. Law number two is the difference law. It says that limit of a difference is the difference of limits. Law number three is a constant times a function. Limit of a constant times a function is the constant times the limit. The constant can be moved outside the limit. Law number four is the product law. Limit of a product is the product of limits. Law number five is the quotient law. Limit of a quotient is quotient of limits. Of course, the limit in the denominator cannot be zero. Otherwise, a number divided by zero is not computable. Law number six. This law is a power law. It says that limit of a power is the power of the limit. Law number seven is a root law. Limit of a root is the root of the limit. Law number eight. Law number eight is the most powerful law. This law is much more powerful than the laws above. Because this law is so powerful, the book gives it a special name. The book calls this law direct substitution. This law says that to compute a limit is easy. Just directly plug in the point A in X. In other words, to compute a limit, we just need to compute the function value at the point A. Of course, the function may not be defined at the point A. When f of A is not defined or not computable, in that case, we need to simplify the function first, then apply this law again. Now, take a look at some examples about how to use limit laws to find limits. Example one, evaluate this limit by limit laws. For this example, I present two solutions. In solution one, I use only laws number 1 to number 7. And in solution 2, I use only the direct substitution, law number 8. Now, solution 1. By difference and summation laws, I can split this limit into this limit minus this limit plus this limit. Then by constant times a function law, I can move constant 2 outside this limit and constant number 3 outside this limit. to get this equation. For this limit, I can apply the power law. Limit of a power is power of the limit. Now, in this equation, we have 1, 2, and 3. 3 limits to evaluate. But these 3 limits are simple enough to tell. As x approaches the number 5, what number x will approach? Of course, will approach 5. Therefore, this limit is 5. 5. This limit, the same limit, 5. This limit of a constant as x approaches the number 5. What number the constant 4 will approach? It is 4. So this limit is 4. Now, calculator, we get 39. So, as x approaches the number 5, this polynomial will approach 39. Now, the second solution. In this solution, I use only direct substitution, law number 8. By law number 8, to find this limit, we just need to plug in 5 in x. So this limit is this number. It is 39. Compare these two solutions, we can see that direct substitution allows us to skip these 3 steps in solution 1 and directly arrive at the last 2 equations. So direct substitution saves us a lot of time and a lot of details. Here, there is one notation. Let me explain this notation. This notation means evaluate this function at 5 or plug in 5 in x. Example 2. Evaluate this limit by limit laws. Again, for this example, I present 2 solutions. In solution 1, I use only laws number 1 to number 7. And in solution 2, I use law number 8 only. Law number 8 is direct substitution. Okay, now solution 1. Because the function is a quotient, so I can apply the quotient law to compute this limit. By quotient law, limit of a quotient is quotient of the 2 limits. To simplify the limits, to simplify these 2 limits, we can use summation law, difference law, and difference law here. So we have this equation. I can see that some limits are constant times a function, constant times a function. So I can move the constants outside the limits. So we have this equation. X to the third, x squared, they are power functions. So I can apply power law to them to get this equation. Okay, now we have 1, 2, 3, 4, 5 limits to determine, but these limits are simple enough. As x approaches -2, what number the function x will approach? Of course, -2. So this limit is -2. This is a -2. And this limit of a constant, as x approaches -2, what number the function 1 constant will approach? Will approach 1. So the limit is 1. So yeah, limit as x approaches -2, what number the constant 5 will approach? 5, the limit is 5. And the last limit is -2. So by calculator, this number is -1/11. So as x approaches -2, this function will approach -1/11. Now, solution 2. In this solution, I use direct substitution to find the limit. By direct substitution, to find this limit, I just need to plug in -2 in x. The rotation is this rotation. This rotation means evaluate the function at -2 or plug in -2 in x. So this limit is this number. This number is -1/11. Compare solution 2 to solution 1. We can see that direct substitution allows us to skip these 4 steps and directly arrive at the last 2 steps. So direct substitution saves us a lot of time and a lot of details. Topic number 2, more examples about direct substitution. From the last 2 examples, we saw that laws number 1 to number 7 is the same with law number 8 in computation. So from now on, we shall only focus on law number 8. In particular, in exams, in your homeworks, you can use only law number 8. You don't need to use laws number 1 to number 7. So you can only use direct substitution to compute a limit in exams, in homeworks. Example 1, under the topic number 2. Evaluate this limit. The solution is simple by direct substitution. To find this limit, directly plug in the number 1 in t. Then we have this number. This number is 3/7. So as t approaches the number 1, this function will approach 3/7. Example 2. Evaluate the limit by a numerical method, then by an analytical method. By a numerical method means by a table. By an analytical method means by limit laws. Here is my solution to question A. In the solution, I make this table. The first column of the table is for the independent variable x. Second column for the numerator of the function. The third column for the denominator of the function. Then the last column is for the function. Now I let x approach the point 5 by taking on these numbers. Then I use calculator to evaluate the values of numerator, denominator, and the function at these points. For example, when x is 6, the value of numerator is 6 squared minus 6 times 6 plus 5 is 5. The value of denominator is 6 minus 5. It is 1. The function value is numerator over denominator. It is 5 over 1. So function value as 6 is 5. From this table, we can see that as x is getting closer and closer to the point 5, numerator is approaching the number 0. Denominator is also approaching the number 0. But their ratio, numerator over denominator, the ratio is the function. The function is approaching the number 4. So therefore, this limit is 4. As x approaches the number 5, the function approaches the number 4. Now, I answer question B. Find the limit by an analytical method. That is, find the limit by limit laws. I only focus on law number 8, direct substitution. Before I present my solution, take a review about law number 8. Here is law number 8, direct substitution. This law says that to compute a limit, we just need to plug in the point A in x. That is, the limit is equal to the function value at the point A. In some case, function value at the point A is not defined or not computable. In the case, we need to simplify the function, then apply direct substitution again. Now, go back to the solution to part B. To find this limit, I plug in the number 5 in x. Then I have this number. This number is 0 over 0, not computable. Some people may then suggest that this limit doesn't exist. But from part A, by a table, we have seen that the limit exists. The value is 4. Now the question is, how to determine this limit to be 4 without using a table, but by analytical method, that is, by direct substitution. How to determine this limit by direct substitution? To find a limit, we need to simplify the function. How to simplify this function? By factorization. We factor the polynomial in the numerator as x minus 5 times x minus 1. Then cancel x minus 5 from the numerator and from the denominator. Then this function is simplified as x minus 1. So this limit is equal to this limit. Now, how to tell this limit? Direct substitution. Plug in 5 in x, then we get 5 minus 1. It is 4. So 4 is this limit. Here is one remark about this equation. Let me let f below this function and let g below this function. Yeah, here. Let f be this function. This function is this function. G be this function. This function is this function. About these two functions, f and g, they are equal everywhere except at the point 5. For example, when you plug in 6, the number 6 in all the x, then it's easy to see that the function value of f at point 6 is equal to the function value of g at point 6. At point 5, however, function f is not defined. When you plug in 5 in the x here, then you will get 0 over 0, not computable. So function f is not defined at point 5. But function g is defined at point 5. When you plug in 5 in the x here, then function value of g at 5 is 5 minus 1. It is 4. So therefore, function f and function g, they are different functions. They equal everywhere except at point 5. Now the question is, this function and this function different. Why we still can have this equation? To answer the question, we need to recall the conventions about a limit. One of the conventions says that as x approaches the point 5, in this approaching process, x is not equal to 5. So when x is not equal to 5, this function, function f, is equal to this function, function g. So we have this equation. As x approaches 5, x minus 1 will approach the number 4. So therefore, this limit is number 4. Example 3. Find this limit by a numerical method, then by an analytical method. To answer question A, I make this table. The first column is for the independent variable h. Second column is for the numerator of the function. The third column is the denominator of the function, and the last column is the function. Now, from this table, we can see that as h is approaching the number 0, the function is approaching 12. Therefore, 12 is the limit. Now, part B. Part B requires us to use limit laws to find the limit. Again, I only use law number 8, direct substitution. By direct substitution, to find this limit, I plug in 0 in h, then I have this number. But this number is 0 over 0, not computable. Not computable doesn't mean the limit doesn't exist. From part A, we have seen that the limit is 12. Now, how to determine this limit is 12? We need to simplify the function. This time, I simplify the function by expanding this power. We can use this formula to expand this power. This formula is easy to verify. Write the left-hand side, a plus b to the third, as a plus b times a plus b times a plus b. Then expand these two products by distribution. Then combine the like terms. We will have the right-hand side here. By this formula, the power 2 plus h to the third can be expanded into this sum. Now, simplify the coefficients. Then we have this equation. Cancel the number A, then we have this equation. Notice that all the three terms in the numerator have h as a common factor. So we can factor h out to get this equation. Now, cancel h from the top and from the bottom. Then we have this equation. Now, for this limit, we can use direct substitution again. Plug in 0 in h, then we get this limit is this number. This number is 12. So 12 is the limit, the value of this limit.